your heading over here. You don't need to write this down. This was just to get you thinking about what you've been doing so far. I've been emphasizing that there's a connection between the normal distribution and functions. And if you ever study mathematics or actually any kind of science course at university, you'll probably see this equation in some respects. Because the normal distribution, I was just kind of racking my head over like, why is this something that's important to you guys? Like, what's so special about the normal distribution? Now, the mathematics behind why the normal distribution appears so frequently is a bit out of the scope of the course. It's related to something called the central limit theorem. Basically, in science, when you take like samples of things, right? The more and more samples of these things that you take, it tends to be become a normal distribution when you sort of do a bit of adjusting. And that's because like usually there's some kind of average and then like small adjustments happen after that. So if you think about like height, like typically there's an average height that people have, and then we have variations based on genetics or, you know, like maybe sport or what other kind of things you do, right? So that's the kind of idea behind it, right? Here's another example. These are distribution of Atar aggregate scores, right? So you can see like, although it's not perfectly that bell curve shape that we're used to seeing, there are these kind of jagged peaks here. The idea is that a lot of these things that we take typically resemble a normal distribution in some respects, that bell curve, distinct bell curve shape that you're used to seeing, right? The aggregate score is a good question. So your Atar is calculated based off an aggregate. So each of your courses, you'll get a mark out of 100, right? Which then each of those units that you do is worth 50 marks. Because for some people they may do 11 units, right? So that's why they've separated each thing into 50 marks so that, for example, if one of your 2-unit subjects isn't as good as your 1-unit subject, then you get half of that 2-unit subject. So each of those single units is worth 50 marks. And basically you're going to get a score out of 500, and that does translate to your Atar in some respects. There is some other adjustment calculation because like we've established, 50 in one subject is not equivalent to 50 in another subject. So in fact, there's another equation that makes some adjustments based on that. It's just mathematics is just everywhere, isn't it beautiful, right? So this is an equation that sort of discusses how they make, I don't know if it's scaling, but they do some adjustments with the aggregate and your actual Atar as well. So even the aggregate itself, like two people can have very similar aggregates or identical aggregates, but they won't have the same Atar, for example. Yeah, okay. Cool. All right. In your textbooks, there are a few common ones. There are 3 common ones that we're going to look at in this exercise. We're going to look at drawing normal distributions. We're going to look at finding areas on the curve using the table. Now, you've already looked at finding the area under a PDF, right? But because this is content with the mathematics standard course, you will also be required to use what we call the table method for the normal distribution, which I will show you. And the idea is that although you have this more advanced level of calculation, you also have to be quite aware of this level of calculation, which is in some sense easier, but then if you don't kind of practice this skill, then you might find that difficult to apply in an exam. Yeah. So finding areas under the curve. But the converse of that is, okay, I know how to find the areas under the curve, but what if I want to find the z-score that gives me that kind of area, if that makes sense. So it's kind of reversing the problem. So if I was asking you, okay, if I give you a z-score, tell me how much area is under that curve, but I can also reverse that question, right? So find the z-score which gives a certain area. These are the 3 main types of questions we're going to look at today, okay? So this first kind of question, drawing normal distributions, I'm not going to spend too long on this because if you have a good understanding of how the normal distributions work, then this is a skill which is just kind of translating the information into a visual sense, right? Because we know what are the important things for a normal distribution. We have our mean, which is going to be something, and we have our standard deviation. And the idea with a normal distribution is that you have your peak, and that's the mean value. And then each time when you go one step away, right, that's, you know, plus 1 standard deviation or plus 2 standard deviations. And if I'm going the other way, same idea. I'm taking away 1 standard deviation, I'm taking away 2 standard deviations. And that's what it would look like in a general sense. But what they may do is they may give you certain values, right? So let's say that they give you a mean of 8.3 and a standard deviation of 1.2, right? They may ask you to draw a visual representation of this. So all you'd have to do is you say, okay, well, I know the values now. Like my mean is 8.3. And then you just have to add along each standard deviation each time. So, you get 9.5, 10.7. Harry, do you want to do the rest of these for me? What values would you get after that? Yep. That's about right. So the question for here, something like this would be, e.g., draw a normal distribution given this information. Now, I'm going to give you a sheet at the end of this lesson, which will show you, which is the table that we're talking about. But the table, let me just give you an idea of what I'm talking about here. Looks like this. Now, last time I showed you this game sheet called the wall. That's that kind of resembles a normal distribution. It's called a Galton board. Now I'm going to show you the wall of text, which is the normal distribution table, and it's this. Now, when I first looked at this, I was like, what is going on here? Why are there so many numbers, right? Well, what this is, year 12, is that essentially, if you think back to what z-scores actually are, the z-scores are how far away a value is from the mean, right? So for example, we said this was a z-score of 1, or we said this was a z-score of 2. But if I was going the other way, this was -1, or this was -2, right? So to see how this table works, I think the best way to think about it is, what's the z-score of the average? What's the z-score of the thing in the middle? 0, because it's 0 standard deviations away from the mean. And if you think about the area under the curve, right? The area under the curve for a z-score of 0, how much of the area should there be? Oh, because the whole area is 1. This whole thing is 1. So the half of it should be, which is half, right? And so if I go to this table, and if you look at this z-score here, you can see there's a column and a row. I'll explain that in a second. But you can see that at a z-score of 0, it's 0.5. So what the table tells you is the area under the curve until that point, until that z-score, for your normal distribution. So it only works for a normal distribution, and it only works for the sort of cumulative area. So the area under the curve until that point. Yeah. So how do we summarize this? Well, let's summarize it like this. We've got 3 steps. So the first step, for p of z of a z-score less than or equal to, or less than, that's equal, right, to a certain value, we use the left column for the first digit, right? Use the left column for the first digit. And then what do you reckon you're going to use the row for, Harry? The next digit. Oh, brilliant. Now, the thing that you need to keep in mind is that this is only going to work for z is less than or equal to, right? For example, let's just go to the higher values here, and you'll see very clearly that, as you go z-scores along, what would you expect? So as you're going to higher values of the z-score, we're going to get really close to 1, because that's basically trying to encompass all of the area. Whereas if I go to the negative z-scores, right, you can see that it's a very small percentage, because we have only these little tail end sections over here, right? So you can see the comparison between those two there. Although the normal distribution is symmetrical, when you choose the negative z-score values, you're going to get a very small percentage. With the positive ones, you're going to get a very large percentage. Yep. So what that means is, if you're asked to find something like this, right, you're going to have to make adjustments. Why? Because the inequality sign is different, right? If I'm asked to find z greater than or equal to something, I'm going to have to do something different. And they can give any kind of variety as well. Maybe they want things in between certain sections. Yeah. Okay. How would you do something like this out of curiosity? Any thoughts on that? Because I've said the table only works for z less than or equal to, but if they ask for z greater than or equal to something, like, I don't know, 1. So I asked for these ones. How might you do that? Yeah, well, a clue is that these are symmetrical, right? So can you see, because our normal distribution is symmetrical, finding z greater than or equal to 1 is actually the same as, you know, if you said z greater than or equal to 1, that's the same as 1 minus p of z less than or equal to negative 1. Wait, yeah. Well, actually, it's the same as, the same as that, actually. So the idea is that p of z greater than or equal to 1 will be the same as z less than or equal to minus 1. Right, does that make sense? Because these are symmetrical kind of distributions. So the idea is that you could use it to find the same thing. And z less than or equal to 1, if you wanted to find it, would be z less than or equal to 1, so 1.0 would be over here. So that one there, right, for example. Okay?